Да.
Женя, вы меня слышите?
Я вас слышу.
Отлично, хорошо, чтобы я...
Да.
Ага, все, хорошо. Ладно, давайте... let us begin. Our today's speaker is Anton Zabrodin from
Skolkovo Institute.
From Skolkovo, yes. Okay, let it be Skolkovo. From Skolkovo, and he's the topic of his talk is Kadomtsev-Petviashvili hierarchies of types B and C. Okay, so you're welcome. Do not forget to switch off your microphones.
Okay, I will speak about integrable hierarchies of partial nonlinear differential equations of Kadomtsev-Petviashvili type. And I will start with this usual Kadomtsev-Petviashvili hierarchy, just to remind you the main facts, which I will need later. And the main object in SATA formulation of the hierarchy is the L operator, which is pseudo-differential operator of the following form. In general, this is an infinite series in negative powers of differential operator, GDEq. Let me also introduce the differential operators BK, which are obtained as follows. We take kth power of this L operator and separate positive part, which means that positive part of Laurent series is just the differential part of this series. Non-negative. And the evolution equations, we introduce the set of infinite set of parameters, which are called times, T1, T2, T3, and so on. This is bold T. And introduce the evolution with respect to these times by the following Lax equations.
BK or B0?
BK. BK. This is the differential operator of order K. For example, B1 is just dx. So the first, the Lax equation with respect to T1 means that dt1 of L is dx of L, and we look here, and this means that we this set of equations means that dx of u j is dt1 of uj is dx of uj for any coefficient, which are originally they are functions of x, but according to these equations, they become functions of all times also. And the dependence on the first time is very simple. Because of this equation, we see that the vector fields dx and dt1 are the same. So this means that the evolution with respect to t1 is just a shift of x. The evolution with respect to higher times are more complicated, and this is just the subject of the theory to study this evolution. And for example, B2 is the second order differential operator of this form. B3 is of third order plus some W, which is expressed through U1 and U2. A compatibility condition of these Lax equations is the so-called zero curvature equations, or Zakharov-Shabat equations, which have the following form. For all K and L. For example, when K is 2, the first non-trivial case, K is 2 and L is 3, we obtain from this condition, if we substitute here these differential operators, we obtain from this condition by equating to 0 coefficients in front of different powers of differential operator, we obtain the famous Kadomtsev-Petviashvili or simply KP equation, which is, let me denote U1 simply by U. And the equation is something like this is well-known KP equation. Actually, when we obtain a system of two equations for U1 and W, but W can be excluded from this system, and the resulting equation is just a single equation of this form. Okay, this is just one possible approach to the theory of KP equation. And we can also introduce a so-called dressing operator W, which is a series of this form. Such that the Lax operator is W dx W inverse W. So this is interpreted as dressing of the differential operator by the dressing operator. Of course, coefficients Uj are expressed through these coefficients Xi. And these Zakharov-Shabat equations are compatibility conditions for the following linear problems for wave function psi. If we require that they are satisfied for all k, the compatibility condition is just this. And the function psi is the result of action of this dressing operator to the simple exponent. It is psi of Tz, where I introduce the notation it depends on the spectral parameter Z, which is not does not enter to the linear problem, but it the wave function depends on Z. So this linear equations are satisfied for all Z. So this function psi has the form.
Does it mean that now, well, in this formulation, so you substitute psi and times explicitly enter the right hand side of our equations? I mean here. So you write these evolution equations, yes, dt.
Yes.
And now psi is written in this form, yes? And
Yes.
it means that times will be present in the right hand side, or no?
In the right hand side of what?
Of these evolution equations.
Here?
Yes.
Yes. Everything depends on times. Through the operators BK depend on the coefficients uj, which I started from, the coefficients of the Lax operator, and they depend on all times. So the coefficients of the operator BK also depend on all times.
Yes, that's clear.
And psi also depends on
And
times.
psi now it depends explicitly.
It's not only explicitly, but also implicitly through coefficients of this double.
Yes, implicitly too. Yes.
Mhm.
Okay, yes.
Yes. Yes, the origin of this factor is very simple. When we have the undressed problem, this means that all coefficients uj are just zeros, the most trivial case. When all of them are zeros, this is a possible solution to this equation. And this is a completely undressed situation. And in this case, BK is just case derivative. And this series is absent. The solution to this problems is just this exponent. And what we do, we dress this equation and obtain non-trivial dressed psi function and dressed operator BK. Okay, one can also introduce dual psi function, which is a solution of the transposed linear problem, which means that the transposition is defined as follows. When we have a differential operator of this form, the transposition means this circle means composition, not action of the differential operator to the function, but composition of this is different. This is an operator of multiplication by f, and this is differential. Form adjoint, yes, formal adjoint. So we can consider adjoint of this linear problem. And the dual or adjoint psi function is the action of adjoint of W inverse to the exponent of the following form. One can also show that the whole set of these compatible linear problems is in fact equivalent to the following bilinear relation for psi functions. This is a set of all times, bold T. And this is another set, independent of this T prime. The counter is a big circle around infinity. And this should be true for all values of T and T prime.
This is a condition.
This is an equation, the relation which is equivalent to the set of linear problems. This and adjoint.
There's a corollary of this.
Yeah.
Something like Stokes theorem, no? Something like
The proof is not so simple. It's rather long, so I will not show it now. Just state the make the statement.
Object analytic.
In fact, I define it as a series, just as a formal series.
Okay.
Of course, for actual solutions of the KP equation and other equations of the hierarchy, this function, this series becomes an expansion of some function, of some real function.
But this equation, in fact, okay, I don't ask the proof, but this equation is a corollary of some conditions, something like Stokes condition, yes?
What is Stokes condition?
No, something like it's okay, because this equation, it is what's the reason of this equation? I don't ask you the proof. I just ask you the reason. What's the reason?
The reason, because in fact, I actually don't need it very much.
Okay.
I wrote it just to introduce the tau function and the equation for the tau function, because this is another equivalent formulation of the hierarchy by means of bilinear relations for tau function. So instead of infinite number of dependent variables, this uj, one can introduce just one dependent variable, which is called tau function, and this is a function of all of x and all times.
Like GDEq function.
Yes. And it can be consistently introduced by the following relations. Let me write it here. where this notation means the following shifts of the independent variables. Plus minus. This is a wave function of the adjoint. For adjoint wave function, we have
So you wrote the generating function or no? Right. Generate function x, which depends on all times. It's here.
it is. I write it in this. This t means this set of all infinite set of times.
Ah, okay. Thank you. So here the t is it's a function of infinite set of times.
Yes, x and infinite set of times.
Okay.
Anton,
How to understand this function?
this is the definition of tau function.
This is the definition.
And this is
And this is actually non-trivial that such function exists.
yes, of course. But I mean that the second equation is just a corollary of the first one.
Not quite.
Huh?
Not quite.
Not quite. So for the definition, we need both.
Yes.
So the definition consists of two
Mhm.
equations.
Yes. Again, the proof is rather long.
Proof of what?
Proof that such function exists.
Exists.
Correct. It will be
Mhm.
Yes, it's very strange.
This was for the first time. This was proved in original works by Jimba and Miwa.
Well,
In 19 something like this.
can you explain just in a few words why such a definition? How to guess? What were the reasons to introduce such a function? Well, I know the result. Well, the result is
Now, using this, let me say it in the following way. Using this bilinear relation, we can substitute these two formulas here, and we get a bilinear relation for the tau function, which encodes all equations of the hierarchy. It has the following form.
Yes. But, well, how to guess? Well, we had this function psi, yes? Quite a nice function. Then we introduce in a very complicated way a new function. How to guess that we should do this in such a form?
Don't know.
You don't know.
I don't know.
And these guys do not explain all this.
They don't.
Okay, excuse me.
A good question, and indeed, honestly I don't know the deep reason to explain how to explain these formulas without a proof.
When you write t for in the function psi, it's again any of these or just. You say
Right. What?
in the tau function t, it's any t1 or t2 or t3 or t4.
Yes, this is a number of
Yeah.
all times, yes.
But in the case of function psi, it is the same.
Yes.
It can be any of them.
All of them.
How
All
to
of them.
understand-
All of them.
All of them.
Yes, but how to understand function of infinite? I'm sorry.
Function of infinite number of variables. Why not? Mhm.
Yeah, okay, something projecting. Okay, I'm sorry.
Mhm.
That. Function of infinite number of variables.
Any particular equation contains only finite number of variables, but the whole hierarchy,
Yes, yes, yes.
the higher equations contain more and more variables.
Okay, I see.
Until you don't think about convergence or so.
No.
Consider them as formal constructions, then you encounter no problem. If you start to think about topological,
No, I don't know.
so then
I'm happy with thinking this way.
Okay, and we need some corollary of this general relation. Just expanding it in a Taylor series in difference between t and t prime, when t prime tends to t, we get differential equations for tau function, which are the bilinear equations. And these are equations of the KP hierarchy in the Hirota form. Hirota discovered the bilinear form of before. So first he wrote these bilinear equations, and then Jimba and Miwa showed how to encode them in the general relation of this form.
as I understand, well, Hirota's bilinear equations were the main source for the work of Jimba and Miwa, yes?
Yes, just motivation.
Yes,
Mhm.
motivation.
Mhm. And this, let me write it in a separate place because we will need it later. Let me denote this tau function Kp, because later we will introduce other tau functions for BKP and CKP. This is in fact bilinear. It can be simply reduced to a bilinear form, and it is obtained from this one by choosing a special form of T prime, something like and taking residues. Then instead of this, you get this as a corollary.
We compute residues with such a T prime. And
Yes, yes, yes. Mhm. Okay, so this is in a short form the whole theory of Kadomtsev-Petviashvili hierarchy. And now we will go to its in some sense special cases, which are called hierarchies of B, of types B and C. They are distinguished by imposing certain constraints on the Lax operator. For example, type B, this is the constraint of the following form. And for type C, adjoint, yes. And in fact, these constraints are consistent with the hierarchy only for odd flows. For times with odd indices.
what do you mean consistent with hierarchy?
They are preserved by the hierarchy. If we start the evolution with respect to times, then odd flows preserve this condition and even flows do not. So we should put times with even indices equal to 0 and fix them forever.
Again, a silly question. And are there reasonable conditions which are preserved by even times?
I don't know. Interesting question, but there is nothing in the literature about this, and I don't know. This is a kind of reduction, but it's not a reduction in the sense of reduction to KDV, for example. When we impose or higher KDV, when we impose condition like this, that negative part is 0, and this reduces the number of independent functions to n. For example, in the KDV case, we have only one independent function, this the very first coefficient, and all other coefficients already are functions of this U1. In case of KDV reduction. This reduction is of different kind. There are still infinite number of independent coefficients.
And other reductions of this time, they produce something like Boussinesq.
Yeah. Boussinesq is cube. In terms of dressing operator, this condition means that and this means that W adjoint is inverse to the W. So the evolution equations are the same. If we consider only odd flows. And this constraint is equivalent to the following property of the operators Bk. That Bk is and the sum starts from 1, not from 0. The free term is absent. This is an important property, and in fact, this constraint is equivalent to this property of the operators Bk. The proof is not very difficult, but let me omit it. This is technical. For example, B1 is again dx, and B3 is dx cubed plus 3L1 dx. And here, this constraint is equivalent to the following property. Again, for odd k. This is also for odd k. For example, let me show you the first equation, which is obtained from the zero curvature equation for k equals 5 and L equals 3. The first non-trivial equation.
B-type, yes.
Yeah, let me switch to B-type and left C-type for later.
That means the times are odd, yes? The times are odd.
Odd. And in C also odd.
This is just zero curvature condition. Oh, yes.
And the system is the following. Prime means x, differentiation with respect to x. not very instructive, but this is the simplest equation of the hierarchy.
So the first equation of B
Of B, yeah, this is actually a system of two equations for two variables.
in 3.
Two variables, U and V.
In unknowns, you mean?
Unknowns, yeah, dependent variables, two dependent variables, and three independent variables, X, T3, and T5.
And did it arise independently in some mechanical?
I doubt. Not like KP equation. This one.
Not like it this is something new, and it should be integrable. Yes.
Yeah, it's integrable.
Everything that arises.
Yeah.
Must be integrable.
Integrable.
And the second equation just because it will, what will be the variables? There will be how many unknowns and how many independent.
Two unknowns
In
and three variables.
Here.
Here.
I mean the next one.
The next one.
Yes.
I never saw the next one. Why do we need it?
Just to understand how the dimensions grow.
Ah.
Of course, I don't ask you to write it down. How many independent variables will arise and how many unknown functions?
In B7, we will have UV and another one, W. And times there will be still 3 times.
Still 3.
Still 3. Yes.
And X.
Hmm?
And X.
And X.
So four independent variables.
No, because here are always 3 variables, because there are variables K, L, and X. Only 3.
Only just
But the number of dependent variables is grows, and the number of equations also grows.
Of course, but the number of yes. So if you take two B's, you have you have just these 2 times
and X.
Yeah.
If we take, for example, B5 and B6, we need not B3 at all.
No.
Yeah, we don't need it. No, don't
You
need.
take the 11 and 13 and you yes. Now I understand. But the number of components will
Now we can introduce the psi function by the same formula. It will let me denote TO. This is O from the word odd. This is the set T1, T3, T5, only odd ones. And psi function depends on T odd and Z and is given by the same formula. And the bilinear relation now is as follows. Now there is no adjoint function. The adjoint function is expressed through the original one just by changing the sign of z.
Due to the properties.
And one can introduce a tau function for the BKP hierarchy by the following relation. Where this notation means
Why is Z? Don't understand the notation. Why do you write Z in square brackets?
this is just the notation. Oh, here, no, I'm sorry.
Ah, yes, now I understand. So this is notation for,
Mhm.
okay.
And now the question is how the Kp tau function and Bkp tau function are related. Because they must be related somehow, because the solution of any solution of Bkp hierarchy can be obtained from some special solutions to the Kp hierarchy just by imposing, by fixing the even times and as function of odd times. This will be a solution to the BKP hierarchy. And the question is how tau functions are related.
But well, this is well, when we introduced, say, BKP hierarchy, we imposed much more conditions, not only clarity of even times, but plus this anti-self.
Yeah. This is what I'm talking about. That only some special solutions of the KP hierarchy correspond. Not only. So the set of solutions to the BKP hierarchy is a subset of the set of solutions to the KP hierarchy. And now our aim is to characterize this inclusion in terms of tau function. What conditions one should impose to the tau function to distinguish the solutions to the BKP hierarchy. We begin with the adjoint wave function. And recall that W adjoint of W is W to the -1. No, for BKP, this is not just like this. This is it is dressed by dx of this form. And this is, of course, on the other hand, this adjoint wave function can be expressed in terms of KP tau function. So we have the following relation. Let me denote T dot the following set of times. I just rewrote this relation in terms of KP tau function.
What is dot OT?
Ah, sorry.
I see.
Now let me use this relation for Z1 equals to the minus Z2. Using this relation, which is true for KP tau function, we can rewrite this relation in the following form. expanding it in powers of z.
You mean this is, you rewrote this log equation?
Yes, yes.
No logs.
It can be, if we take this derivative
Oh,
here,
yes,
this derivative can be eliminated with the help of this relation. And we get, after some algebraic transformations, we get this. And this is just the condition for the tau function,
of B.
for Kp tau function, such that
Produces solutions of BK.
yes, which corresponds to solutions of BKP. Expanding it in powers of z, we get first non-trivial relation. This is BKP. And let me say right now about CKP, repeating the similar calculations, doing similar calculations for CKP, we get, instead of this condition, we have the following one. And it can be proved that, in fact, it is necessary and sufficient condition for Kp tau function be the tau function of CKP. I don't know how to prove this, whether this condition is necessary and sufficient for all hierarchy, and here I can prove
So
for
you
CKP.
mean,
For
well,
BKP, I don't
in
know.
spite of the fact that expanding in powers of Z, you obtain infinite number of
Yes,
relations.
yes.
The first one is CKP.
In CKP, yeah, I know that the first one actually implies all higher
And
conditions.
For B, you don't
For B, I don't know.
And isn't it strange that, well, in our world, we kill all odd t's, and nevertheless, in the equation, T2 arises.
Let me stress that this condition does not mean that tau function does not depend on T2. This means that just the first derivative is equal to 0, but the second derivative can be non-zero.
So it depends on T2.
Yes.
But you say in the case.
Yes, but after that, we should put all.
Put T2 equal to 0 and forget about it. Doesn't change it.
You first differentiate and then put T2 and T4 and so on.
Yeah, yes.
And the same for B.
Similar, not the same, but
No, yeah,
similar condition. After differentiation, yes. Yes. How much time do I have?
Well, it's up to you. What usually we, how much do we need? Not to be half an hour.
Okay.
Okay.
So, and one can also prove using this relation that the tau BKP tau function is some constant times square root of Kp tau function. And similar for CKP.
Similar.
But in BKP, this Kp tau function is a full square. So tau function is usually an entire function of all variables. And after taking the square root, we don't obtain square roots branch points. It's a full square. And I will show an example how it later for soliton solutions. For CKP, this is not the case. In general, the right-hand side has branch points.
Change points. Something like Pfaffian.
Yeah, it's like Pfaffian. Yeah, exactly. And for CKP, the relation between psi function and tau function is not so simple as for BKP. For CKP, we have the following: psi is given by such a formula. Where G,
This is X or multiplication.
this is multiplication. More complicated relation between tau function and psi function in CKP. Okay, now let me show some examples of solutions. Namely, soliton solutions.
Of the entire hierarchy.
Yes. The general Kp tau and solitons of BKP and CKP are special cases of 2n solitons of Kp. And for Kp, the formula for n soliton for tau function of the n soliton solution is as follows. And let me denote this tau function in the following way. It has parameters alpha 1, alpha 2, alpha 3, alpha 4, P1, Q1, P2, Q2, P3, Q3, 4, 4.
Who are these P and Q?
They are called momenta of solitons.
Yes,
They are just
Yes.
parameters, free parameters.
just parameters.
Yeah. So there are all of them, all of these
Ah.
numbers are just free parameters.
Ah,
And the independent variables are here.
yes, so they're just like velocity or something. So moment. Okay.
And square bracket, what it means?
Just the notation that this tau function depends on these guys as on parameters.
And when you talked about square, it didn't appear yet. Next example. You talked last 5 minutes ago about square.
Yeah. I will show. I will show for n equals 1 example of this. And for BKP, one should choose these parameters in the following way. So you see that these are opposite, choose equivalent opposite, and these are opposite.
Yes, I did not. Yes. So
They correspond to this.
the pairs are not independent.
Not independent. Yeah, the number of independent parameters is less.
Something like Fluker or no here.
Uh,
Sorry, just
In fact, the bilinear relations for tau function is another form to write Fluker relations.
okay. So I see.
Mhm.
So it relates to these infinite Grassmannians.
Yes, yes,
Ah,
yes,
it's
yes.
related with
Of course,
Grassmann.
Yes.
because the solutions in this
Thanks.
language I interpreted as.
It is why, yes. No.
And it can be shown that this determinant is a full square, full
okay.
square of Pfaffian.
Full square perfect. Okay. But determine what type of what determine how you
Let me
determine.
show you example.
Yes.
N equals one soliton solution. Where W is and you can see that this is a full square. This is just this formula without this only this part. And for CKP,
So this is one soliton for BKP.
one soliton, yes, for BKP. And for CKP, one soliton is the following.
You need to look up your square roots of these.
Yeah. This is Kp tau function, and BKP tau function is square root of this, and CKP tau function is square root of this. But this is not full square.
No.
So CKP is not, you have not this property in the case of CKP.
No, it doesn't have. Alpha n.
And do you know some, oh, sorry. Do you know some explanation of this property or no? Why it appears? Because there are so many reasons why if something square root you can take it, it has to be. Are there some reasons or research?
I think yes, but I cannot explain it because B is related to B series of Lie algebras.
Okay.
This is SO algebras with antisymmetric matrices.
Yes, okay.
And for antisymmetric matrices of even size, we have Pfaffians.
So
The determinant is a full square.
it's very.
I think the deep reason is this.
Okay, thank you.
But it's not it's not simple to recognize it from what I told you. Okay, so I think this is almost all what I had. Don't know. I gave examples, representative examples of solutions. So I think this is all.
Thank you very much.
Thank you.
Questions, remarks? Well, can you hear me? Жень, меня слышно?
Unable to hear you.
Questions, remarks, comments? No. Anton, thanks a lot again. So this seems to be our last meeting in this semester, and I wish everyone to have a good and nice summer
Without COVID.
And thank you for participating in our seminar, and we'll be glad to see you in September again. Goodbye.